Hello, my name is Emmanuel Mendez, and in this project, we focus on an engineering problem related to steam piping system, which are commonly used on power plants and industrial facilities. These pipes transport steam at very high temperatures, and as the metal heats up, it experiences linear thermal expansion. This means that the pipe increases its length and as the temperature rises. And if this expansion is not managed correctly, it can create serious structural issues, such as high internal stresses or maybe failures in the connection flange, or even the bending of the pipe. And these complications can interrupt operations, damage equipment, and pose the safety risks. For that reason, engineers need to understand how fast the length of the pipe is changing at any given moment. And in our project, we use differential calculus to calculate the instantaneous rate of change of the pipe's length with the respect of time. This value is essential for designing supports, anchors, and expansion joints that allow the system to expand safely as the plant begins operating. So in conclusion, calculating this rate helps to prevent failures and ensures the reliability and safety of the entire steam piping system.
Hi, I'm Diego, and so you may ask, what is the relation between the engineering programs and this specific problem? Well, the relation with IMA and IME is that both careers deal with different material behaviors, like in this case, the thermal expansion and its analysis. But in IMA, we will specialize more on the dimensional changes caused by the temperature, and in IME, they will look out for the energy transference. In IMT, or Engineering in Materials, it is related to the study of microstructures, the thermomechanics, the prediction of thermal deformations, and the mechanical properties of the metal, like in this case, that is the carbon steel.
Hi, my name is Kiara, and as Emmanuel said, we're going to have to calculate this problem that we use, which we need to find the instantaneous rate of change of the pipe's length at a specific moment. In this case, will be 30 seconds. This is to ensure the pipe's expansion joints and supports are designed correctly. Now, in engineering, materials expand when heated, and this is called thermal expansion. And now, we have that the length of our pipe depends on its temperature. And since temperature is constantly rising over time, the length is also changing over time. So, we're going to start with the basic formula for the pipe's length, which is this one. And first I'm going to say this represent. The L is the length, this L is the initial length. This alpha term is a constant, which is this one was investigated on internet of the carbon steel that it's used on the pipe that in our problem has, and this is only the change of temperature during this 30 seconds. Now, since we want to know the speed at which the pipe is growing, in physics, speed is the rate of change of position. But in calculus, the rate of change is the derivative. So our goal is to find the rate of change of length with respect of time. Now, since length depends on temperature and temperature depends on time, we use a chain rule to link them. So the derivative simplifies the main formula into this one that we have right here. What does this mean? The speed at which the pipe grows here is found by multiplying three things. First, we have how long the pipe is, then how much the material naturally expands, and then how fast the temperature is rising. Now what we have to do is to find the rate of heating. So we are given the temperature function, which is this one right here, and we need we need its derivative of dt over time, which tells us how fast the temperature is rising at any moment. So we're going to do just that. So it will be 0.5 plus 0.02 times time. So we're checking at time at 30 seconds, which 30 seconds is 0.5 minutes. So we're going to just change t to 0.5 minutes. So it will be 0.5 plus 0.02 times 0.5 minutes in here. This will give us the 0.51 grade Celsius over a minute. This because at 30 seconds the pipe is heating up at a rate of 0.51 degrees Celsius per minute. Now what we have to do is to find the rate of expansion. Here we have it. Now what we do is to plug this heating rate into our main rate formula. So dl over dt equals the initial length times alpha, which is the constant, and times dt over time. And we're going to use the numbers that we have. So it will be the initial 50 meters, the length of our pipe, times 12 times 10 to the minus 6 Celsius grades, and times 0.51 Celsius over minute. This is important to say. This was found in the internet, which is for the rate of expansion for the steel that it's used on our pipes. So we're just going to calculate this, and this will finally give us the 0.000306 meters over minute. So this we're just going to divide it. So instead of meters, it's going to give us the millimeters over each minute. So doing those calculation will give us the 0.306 millimeters of expansion per minute at a time of 30 seconds. And this will be the final result.
Hi, I'm David Garcia, and I'm going to tell you the conclusion that we came to for this problem. First of all, we know that the derivative is used to explain the instantaneous rate of change for the growth of the pipe length at a specific moment. In this case, that'll be 30 seconds after the start of the process. Now, by differentiating the temperature from the time of the reaction, we were able to determine what's the exact length of expansion. It also works as a tool for predicting the behavior of the material and as it changes its temperature. In this case, the rate of change after 30 seconds is 0.306 millimeters per minute for this specific material.
Hello, my name is Matias Chapia, and I'm going to be talking about the careers conclusion. So we had 3 careers in our team. The first one being the electromechanical engineering. This engineering contributes with the mechanical and electrical systems and the basic knowledge of it. they can calculate, like in this problem, with the expansion of, or the expansion rate of a pipe, they can calculate like the thermal expansion, the heat transfer, and all of that, and will ensure that the equipment works efficiently. Then we have mechanical administrative, which is like a combination of engineering knowledge and with administrative skills like resources, cost, logistics, and well, in the case of the expansion of rate of a pipe, they make sure that the technical analysis fit into a realistic financial or operational plan. Then we have materials engineering, which are engineers that analyze the materials like the metals, polymers, and they also calculate the temperature, the stress, and also the corrosion of the materials. And well, in the problem, they can determine like whether carbon is appropriate or how much it can be deformed and all of that. And well, these three engineering fields are very important because they ensure that the systems work as efficient as it should be. They can make systems that operate safely, efficiently, and within an economic budget.